Okay, today we're going to cover the first of our 2 days on the fundamental theorem of calculus. Recall from the previous section that we have the integral from a to b of f of x dx. This is standing for a certain type of limit. This is the limit of what's called the Riemann sums as the number of rectangles goes to infinity. Right? And it doesn't matter what type of sum we use, whether it's the left-hand sum, the right-hand sum, midpoint, max, min, right? We're all supposed to get the same limit out of this. Okay, so that's what we mean by the integral from a to b of f of x dx. Now, before we learn the fundamental theorem, actually computing something like this is a very difficult process, right? This is not an easy thing to figure out how one would compute, right? Because we've got many rectangles, and the computational power alone makes it seem like we're never ever going to be able to calculate these things. But that's the beauty of the fundamental theorem, and I'm going to write it down. It's going to tell us, at least sometimes, how we can very quickly figure out what this limit is. This is theorem 5.1. This is known as the fundamental theorem of calculus. And it says the following. If a function f is continuous on an interval ab, a closed interval ab, and f of t happens to be the derivative of some other function, capital F. So I'm using capital F as the function whose derivative is little f of t. For some function, capital F of t, then the integral from a to b of the function little f of t dt, or rather I should use x here, t is a dummy variable, f of x dx, is capital F at b minus capital F at A. So to actually calculate this limit of Riemann sums as the number of rectangles goes to infinity, all we need is a function whose derivative is the function we're trying to take the integral of. Here's one very quick example to confirm what's going on here. Let's do the integral from 0 to 5 of 2x dx. Now, here, little f is 2 times t. That's the function we're taking the integral of. Big F is the function x squared, right? Because big F's derivative is 2x, which is the same thing as little f. So this matches the definition from the theorem, or this matches the statement of the theorem. And so that means that I can calculate this limit, this definite integral, by saying this is capital F at 5 minus capital F at 0. Capital F at 5 is 5 squared. Capital F at 0 is 0 squared. So this is 25. So rather than having to actually deal with this limit, we can quickly compute what these integrals are, which is pretty great. Okay, now we're going to talk a little bit more about what these integrals actually mean by doing some word problems and talking about things like that. Let's do a word problem here. Let capital F of t represent a bacteria which has population 5 million at time t equals 0. After T hours, the population growth is at rate 2 to the T million bacteria per hour. Estimate the total increase after the first hour and the total population at time 1. Okay, so we have to take a look and figure out what's going on here. Okay, so capital F of T is the amount of bacteria that are there. Capital F prime of T is stated to be equal to 2 to the T million bacteria per hour. Okay. So if we were to calculate the integral from 0 to 1 of 2 to the T dt, this would tell us the increase over the first hour of what's going on here. This would be the increase over the first hour of bacteria. This would be the new bacteria. First hour. Now, the question is there a function whose derivative is 2 to the T? If we could find such a function, then we would be able to calculate what this new bacteria over the first hour would be. And the answer is yes, there is. Let's call this function g. It is 1 over the natural log of 2 times 2 to the T. Because when you take the derivative of 2 to the T, you get 2 to the T times the natural log of 2. And so these natural logs of 2 will cancel and leave us with the original 2 to the T. So, using the fundamental theorem, I can say that this integral from 0 to 1 of 2 to the T dt is going to be g at 1 minus g at 0, which, now we can calculate this. This is 2 to the first over natural log of 2 minus 2 to the 0 over natural log of 2. So this is equal to 2 over log 2 minus 1 over log 2. This is equal to 1 over log 2, which is around 1.44 million bacteria. Because it's 1.44, so it's 1.44 million because this is in bacteria, million bacteria. So that's the new bacteria. And remember, we started with 5 million, so the total population, 5 million plus 1.44 million, which is 6.44 million. So when you integrate a rate, you get a total. Okay, let's take a look at another one of these word problems. Okay, pollution is running into a lake on day t at a rate of f of t kilograms per day. So one question we could ask is, what does little f of 12 equal 500 mean? Well, little f is the rate that pollution is running into the lake at that day, and little f of 12 equals 500 means that on day 12, 500 kilograms of pollution is entering the lake. Or actually, more precisely, on day 12, the rate at which pollution is entering the lake is 500 kilograms per day. These are two slightly different things, but usually we conflate those two things. Okay, second question. What does the integral from 5 to 15 of little f of t dt equals 4,000 mean in this context? What would that mean? Okay, well, we're integrating from 5 to 15, so that means this is a statement on something that's happening between day 5 and 15. And we're integrating a rate, a kilogram per day rate. And when you integrate a kilogram per day rate over days, you get a total kilogram rate. So this means that from day 5 to day 15, a total of 4,000 kilograms of pollution entered the lake. Okay. That'll be all we talk about with that problem. Okay. Let's see, what more to say today? Let's just do a few more examples here. Let's integrate from 1 to 7 x squared dx. Okay, so from before we would think this is a very complicated problem. But if we note that the derivative of 1/3 x cubed is exactly the function x squared, this allows us, via the fundamental theorem, to immediately say that this is 1/3 of 7 cubed minus 1/3 of 1 cubed. Okay? So that allows us to say we get 7 cubed over 3 minus 1/3. So this is 7 cubed minus 1 over 3. All right, 7 cubed is not coming to me in my head here. I'm going to have to, so 7 times 7 times 7 is 343. Okay, so this is 343 minus 1 over 3. So this is 342 over 3. Which I believe will reduce even further, right? 3 into 342, we get 1, 1, 4. Okay, so this is 114. Okay. We didn't have to draw any rectangles. We didn't have to take any sampling of a function, anything like that. Okay, this just comes out purely because of the fundamental theorem. Okay, so I'm going to have some problems on a worksheet, as usual, which you'll take care of in a few minutes. And then on the next video, part 2 of this lesson, I'm going to talk about why this theorem is true. I'm going to try to sketch a proof of this theorem for you. This fundamental theorem, right, it is a pretty crazy statement. Why on earth would we believe this statement to be true? I'm sure most of you have no problem using this theorem, but some of you might be puzzling, why does this work like this? And I think it's actually something that you can understand at this level, and I want to give a brief discussion about why that is the case. So I hope you're able to join us for that, and looking forward to it.